Okay, here we have a uniform density sphere, perfectly spherical. We'll call it a planet. And it has a tunnel drilled all the way through, in this case, to the other side. We're going to move this thing around, but for now, the tunnel is a diameter, goes straight through. We have an object that we're going to drop into this tunnel, and we want to know what it's going to do. So there's no friction, no air resistance, nothing like that. The only thing that's going to affect this motion or cause the motion is gravity. Now, you have to know that the gravitational force inside a uniform sphere varies linearly with the distance from the center. So the farther away you are from the center, the stronger it is up to the surface here. And if you double the distance, you'll have double the force. That's what linear means. It's directly, but the force is directly proportional to the distance from the center. And it's always aimed toward the center. Now, this is a vector that represents the force, this arrow pointing down toward the center. So the question is, what is this thing going to do when we release it? Now, some people think it won't move. It'll just stay here. Other people think that it will drop down to the center and stay there. Some people think it'll go all the way down to the bottom and stop and stay there. Some think it'll go all the way down the bottom and fall out the other side. So let's see what it does. Now I have a satellite. We'll talk about this later. I'm going to turn that off for now. The satellite is this little guy here, the yellowish one behind the red dot there. That's the satellite. I'm going to turn that off. Let's just focus on what this is going to do. So here we go. Now before I click go here, what do you think this thing is going to do when we hit go? Is it going to move? If so, what is it going to do? Let's try it and see. Here we go. It oscillates back and forth from one end of the tunnel to the other. Just keeps doing that back and forth. Now, if you think about this vector, instead of as a vector, think of it as a spring or a rubber band. Suppose this was a rubber band. Then you can kind of picture how that motion would work. The rubber band stretches as far as it can, and then it pulls back down this way and keeps going like that forever and ever. This is an example of simple harmonic motion, where we have a force that's always directed toward the equilibrium position, which in this case would be at the center. We'll see that in a minute, because I'm going to put it right there and you'll see that it doesn't move. So it has to be directed toward the center, and it has to be linearly proportional to the displacement from the equilibrium position, which here is the center. Now we have that. This situation meets those conditions. So this is simple harmonic motion. And this looks very much like what you would see with a spring mass kind of situation. All right, now let's try something here. Let's take this guy and let's put him right at the center. Let me move the time back to 0. Let's put this guy right at the center and see if I can get him right there. Okay, right on the center. All right. Now I say that's the equilibrium position. The force at the center of this uniform sphere is 0. So if there's no force on it and it's just sitting there, when I click go, it should not move. Let's see. Well, sure enough, see, time is running. The satellite is going. We'll get to that later. That shows you that the program is running, it's doing it, but it's not moving because there's no force acting on it there. All right, so let's reset. Now let's put this guy back. Instead of all the way up, let's put him part way out. Let's go about here. Well, that's about half, right about there. Now, what do you think it's going to do? We couldn't really do this with a tunnel. We wouldn't have the ball halfway down the tunnel, but you know, it's a simulation, so we can do whatever we want. So let's say it's halfway down. Now I hit go. What's it going to do? Is it going to go to the center and stop? Let's see. No, it oscillates just like it did before, except over a shorter distance. Now this time, as you notice, this is just fractions of the period of motion. And there's a PDF with the mathematics of all of this that proves that this period of motion, how long it takes this thing to complete one cycle, to go from, in this case, right here, down and back up to here again. The way I have it set up, it's based on Earth parameters. It's about 80 some minutes, 85 minutes, something like that. But the time scale is arbitrary. Okay, so this is fractions of the period. So it just goes from 0 to 1. But notice that that doesn't change. And actually the satellite's helpful for this. Let's let the satellite here. Let me reset all this. Okay, so the satellite is starting up here. This guy is starting here. And let's let time run and watch what happens to the satellite and this. We'll explain what that satellite's doing later. So when the satellite completes its orbit, this guy is right back to his starting position. Okay? So this guy covered the distance from here to here. Actually, I should probably put some markers in here showing the initial position so you can see where they are. But the length is about from here to about here. Okay, so that's a relatively short distance that it covered in this amount of time. So let's put time back. Now, if we put this guy out to here, I'll turn the satellite off. Okay, so now it's going to cover this whole diameter in the same time. Now, how can it do that? The only way it can do that is if it goes faster. Let's see. Now, there's a way to estimate the average speed. The speed is not constant. In fact, even the acceleration is not constant, so we can't use kinematics formulas. We could figure out the velocity using some calculus, frankly, as probably the simplest way to do it. We can do some calculus and figure out an average speed for this thing. And we'll find, as you would guess, as you can see from watching this, when this distance is longer, this guy is going to go faster to cover that longer distance in the same time, right? See, this time scale is not changing. So this guy is going faster to cover this longest possible distance, in this case. The diameter is as far as it can go. All right, so let's stop it. And let's make, and let me reset time. And let's make the distance it's going to go now is from here down to here. Obviously much smaller than this total diameter. But the time is going to be the same. So this is going to have to move a lot slower. Let's see what happens. Yep. It's moving a lot more slowly now. It's covering the shorter distance in the same time as it previously covered the longer distance at a higher speed. All right. Now there's a couple ways to explain why that's happening that way. One is energy. When let me reset everything again. Wherever we put this, well, let's put it this way. The initial position here that's the equilibrium position. If you displace this, you move it up here somehow, you are doing work. It's just like pulling a spring, or again, pretend like this is a rubber band. If you're pulling a very strong rubber band, you're pulling like crazy to pull this thing up to this height. You're putting energy into this system. Okay, that's potential energy. And then that's going to become kinetic energy when we release it, when we hit go here, and let the equivalent of you letting go of it. And it's going to start moving. So the higher up we go with this, whoops, not like that. Got to do it like this. Okay, we move this guy up like this. We've done more work to pull this guy up to this height than we did to pull him up to this height. Okay, so there's more potential energy in this system waiting to run. And so when we hit go, which is equivalent to releasing this thing, it's going to go pretty fast. And again, we could calculate it and I could print the speed here, but the units are arbitrary. Numbers wouldn't really mean anything. We can just as well tell by looking at it what it's doing. The exact numbers of it don't really matter. There is a way to calculate it. Let me hang on. Let me stop this. Let me get this. Okay, so to there. If we call this x naught, even though it's vertical, you might think it would be y, but it could just as well be. We could turn this diameter horizontally, and then it would look like x the way we usually do. But since this is a sphere, we can rotate it any way we want. It's all going to work exactly the same way. So it's completely arbitrary which way we do this. A diameter is a diameter. It doesn't matter how it's oriented. So I'm going to call this x naught. The displacement from the center up to here is x naught. So what happens is we can use a simple formula. It is from kinematics. I told you a minute ago you can't use kinematics because the acceleration isn't constant. But there's a very simple kinematics formula that we can still use. It will work. And that is that the average velocity is the total distance over the time. So what's the total distance? It's going to be 1x naught down to here, 2x naughts down to the equivalent down here, the negative of this. It's down here. 3x naughts to come back up to here, and then 4x naughts to come back up to the original place. So in one cycle, one complete cycle, it goes through 4x naughts. So the distance is 4x naught, whatever this distance is, divided by the period. And that period is determined by the characteristics of the planet. The gravitational constant, Newton's gravitational constant, the mass of the planet, the radius of it, and so forth. That all factors in to calculate the period of motion. Okay? So the more potential energy we give this, by moving it farther up, the faster this thing is going to go. Because x naught is now larger. That's a way of calculating it. Energy is a good way to look at it, like I mentioned a minute ago. Because you're putting more potential energy in the farther you displace this. Okay, so either way you want to look at it, just 4x naught over big T, that gives you the average speed. So the bigger x naught is, the bigger the speed is, the higher the speed. Or if you want to look at it from energy point of view, the farther up you move it away from equilibrium, the more PE, potential energy, you're putting in, which means when you release it, that's going to go to kinetic energy as it moves, and it's going to move faster. And intuitively, you can picture this like a really sturdy rubber band. You know what would happen if you had a really strong rubber band with something on the end, a rock, and you pulled on that rubber band to pull this thing all the way up to here. You know when you release it, this thing is going to go flying down this way. Now, this doesn't move that fast, but you get the idea. You've seen that in the real world. Okay? So there we go. That's what it does. It's simple harmonic motion between the what I call x naught, the initial position, up and down. Okay, now let's try messing around with this a little bit. Let's set the time back to 0. Let's set this back to 1. Now let's try moving this tunnel a bit and see what we can get. Let's try something like this. How about that? Let's try that. All right, now what do you think it's going to do here? Think about it. Our force is still directed toward the center. That's always going to be true. But as this thing moves, well, let's get ahead of it here. Let's just do it and see what it does and see if you can figure it out. Let's go. Look at what's happening to that force vector. It always points toward the center. This thing is still oscillating between the two endpoints of the tunnel. So let's take a look at this for a second. Let me stop this and let me move this. Let's see, let me move this over like this. Now this force, if you've had vectors in your studies, you know that you can resolve this vector into a component that would be parallel to the tunnel and a component that would be perpendicular to the tunnel. And I'm drawing about where that would be. The perpendicular part would come down to about here, and the parallel part would come over to about here. Now the part that's perpendicular to the tunnel just pulls the ball into the wall of the tunnel and doesn't do anything because it's frictionless. If there was friction, that would be quite important, but there's no friction. So this component that I'm sketching here that comes from here down to about here, that's the majority of the force actually, is going into the wall and it's not really affecting the motion. The part that makes it move is the component of this force that is along this tunnel. Okay, so just picture that. Let this thing go again. Let's watch it. So let's try something. Let's try stopping at what should be the equilibrium position. Let me put time to 0. Put this guy where I think the midpoint should be. Well, actually, it's 0. Right there. Okay? That should be the equilibrium position for this setup. Because all of the force is directed straight down here. It's all into the wall of the tunnel. There's nothing going along the parallel to the tunnel to make it move. So when I click go, that should not move. Let's see. Yep, see, time is running, but it's not going anywhere. Because all the force is directed straight down toward the center. There's nothing left to go along sideways here to give us any motion. So let's reset. Now let's give this guy just a little bit of an offset. Now what do you think it's going to do now? We displaced it from its rest position only a small amount. So x naught was small. 4x naught over big T is constant. So if x naught is small, 4x naught over big T is going to be a relatively small number, which says that it's going to move relatively slowly. Or we can look at it from the potential energy point of view. We only displaced it a little bit from its equilibrium position, so we only put a little bit of potential energy in. So we're only going to get a little bit of kinetic energy out of it. So it should move slowly. Let's see. Yep, moves very slowly. There's not much force going along that tunnel parallel to the tunnel. It's almost all going into the tunnel wall. So it's hardly moving at all. Okay, and reset again, and let's move it a bit farther. Well, all right, let's put it all the way out. Now we've given it a large displacement from the rest position, which is about here. Okay, so we put quite a bit of PE in it. Should go pretty fast this time. Well, faster than it did, certainly. Right? Because it's covering a longer distance in the same time, it has to go faster. All right. Okay, so let's stop right about there. Well, actually, let's just reset and put this guy back in his equilibrium position, which is at 0. Okay, and then if we hit go now, it won't move. Okay, now let's see what else we want to try with this. We've done a full diameter. I guess we could try going up to the top here and making a very short tunnel. Now I haven't changed anything. If I hit go, do you think it'll move? Nope, not moving. Same thing. This is the rest position. All the force is directly down toward the center. It's all into the wall of the tunnel. None of it is going along the tunnel, so there's nothing to make it move. And we haven't displaced it from its equilibrium position to give it any potential energy. Okay, so let's displace it a little bit. Now it doesn't matter either way. About like that. Oh, wait a minute, let me set the time back to 0. Put this guy over here like that. Okay, so we give it a little bit of displacement. We put a little bit of potential energy into it. There should be a little bit of motion. Or if we look at our x naught thing, how far we displaced it, how much work we did that we put into that, our x naught, 4x naught over big T to get the average velocity. X naught's fairly small, over big T, which is the same as it's been the whole time, because that's determined by the planet, it's going to be pretty slow. So let's see. Yep, very slow. Okay, a couple different ways of looking at why that's happening now. The force along the tunnel direction that's making this move is quite small. It's almost all going directly into the wall of the tunnel. Very little of that force is going along the tunnel to make the object move. Okay? Now, let me reset because I want to show you the satellite thing. It's kind of cool. Oops, wait a minute. Let me reset. And let's see. Let me put the tunnel back more like this. And put this guy up here and put the satellite back in. All right, now, if you get the PDF that goes along with this, there's some math, and it discusses something called Kepler's third law. Now, you probably haven't got to that yet in your physics studies, but you will one of these days. It has to do with orbital motion. And it turns out you can prove that the orbital period of this satellite in a low orbit, right, basically just right above the surface, which of course is very unrealistic. Any real planet would have mountains and such and it would crash into, or an atmosphere. We're assuming there's no atmosphere here, there's no mountains, it's perfectly smooth. So this satellite is just barely above the surface. And it can be proved that its period of motion, the time it takes to make one orbit, is the same as the time it takes this guy to make one cycle. Let's see if that works. Well, they meet down there. They should meet up here. Yep. So when this guy's on a diameter, the period of time it takes to do that is equal to the period of time it takes this satellite to go around. That's pretty cool. Now let's stop this. Let's reset. Now let's take the tunnel and move it a little different, make it kind of a different tunnel, much shorter tunnel. Now this should still work because the period of motion should still be the same for this tunnel as it was for the full diameter. Let's see. Doesn't seem possible, but look at this. How about that? It's going to meet, it's going to come back to the same time right there. How about that? So that's the gravity tunnel. Pretty cool.